Hi everyone. Today we are going to start looking at gravitational fields as part of the next area of study we're looking at, which is all to do with fields in general and how they make things move around and how they interact with the objects in our universe. You can read through this yourself. This is just straight from the study design. There's quite a little bit here, but we'll get through it eventually. So this area of study is concerned with three types of fields: gravitational fields, electric fields, and magnetic fields. Today we're going to start looking at gravitational fields. So here's what we're going to look at in this video. We're going to describe gravity, or rather we're going to describe gravitational fields using this field concept, this field model. We're going to look at the shape of gravitational field around a mass, and with what, like how we can describe it in terms of words, I guess, such as uniform or non-uniform, or static or changing. I've highlighted monopoles here. We'll talk more about that later on when we get to magnetism. So we're not going to worry about that word here for today. Okay, so let's start by talking about, first of all, what the hell is a field? All right, so to answer this question, we need to ask ourselves a few more questions to get us thinking. So if you think about it, if you really think about it, how does the Earth exert a force on the moon without being in contact? Okay, really think about that question. Okay, or how does the sun exert a force on the Earth without being in contact? Your everyday experience, okay, you wake up, you get out of bed, you put your feet on the ground, okay, there's a force of contact between your feet and the ground, okay, the normal reaction force. Then you go to open your curtains, all right, you might grab the curtain and pull it aside, okay, the reason why it moves is because you're in contact with it and you are pulling it across. And this pulling action, that's you applying a force, right? Your car breaks down or something, all right, and you've got to push it onto the side of the road. Why does the car move to the side of the road? Why doesn't it just stay on the road? Well, because you're pushing it. You're applying a force, and there's a contact between your hand and the car that's causing it to move. But if you think about, why does anything fall down to the ground when you let it go? It's not exactly clear how that works. Okay? We just take it for granted. Things fall down because of gravity. That's just how it is. Okay? But there's no invisible man holding onto a ball waiting for you to let it go so he can pull it down to the ground. All right? Or at least we don't think so. So how does it work? How does a force become mediated? Or how does one object exert a force on another when they're so far apart, such as the Earth and the Moon, or the Sun and the Earth, when there's no apparent contact between them? Why is there a force there? How does it work? Okay, that's what we're trying to attempt to explain by talking about a field. All right? And you might not get a very satisfactory answer in Year 12. We sort of just explain it by introducing something new which we haven't explained. All right, and if you really want to get into the depths of it, you've got to study general relativity. That's basically how gravity works. If you want to get into electric and magnetic fields, you've got to get into quantum field theory, and that's just getting way out of the scope of Year 12 anyway. Okay, so we're trying to answer, how do things move without contact? That is actually the subtitle of this area of study. Okay, so let's introduce this concept of a field. People introduced this concept 100, 150, 200 years ago to try and explain things. Since then, we've updated our way of thinking, but it's not part of the Year 12 study design. Okay, so what is a field? Or what is a gravitational field, at least? So we're going to describe a gravitational field as a region in which a gravitational force is exerted on all matter in that region. Okay, and I'll show you a couple of videos down here in a second about what that might look like. But basically, if you have any object that has a mass, and we're going to call these massive objects, okay, any object that has mass, okay, so photons don't really count because they don't have any mass, or light doesn't count, but something like Earth, or the moon, or even yourself, okay, each of these things has an associated gravitational field, okay, and what we say is that the gravitational field is exerted out into space. All right, an object with mass exerts its gravitational field out into the space around it and somehow influences the space itself. Okay, and it's really important to know that at least the gravitational field extends out into all regions of space, infinitely far away from the object itself. Okay, but it will get weaker and weaker the further away that you go, and we'll see just how weak when we discover our little formula that we can use to calculate the field strength later on. Okay, so what I'm going to do quickly, I'm going to show you just a couple of videos about what this gravitational field might look like if you were to try and imagine it. Okay, so I'm going to just mute the mic for a second because I'm going to play around with the laptop, so it's going to make a bit of noise. So I'll be back in one moment showing you these couple of videos. Okay, so this first video is going to try and help you visualize what it means for a gravitational field to exist in space. Okay, and we mentioned it's got something to do with how space is modified or we're going to call it warped in a sense. And this is what Einstein is trying to get at with his theory of general relativity. Okay, so what we've got basically here, trying to imagine like a three-dimensional lattice or a three-dimensional grid system. All right, right now, all of these grid lines are equally spaced apart. Everything's nice and straight lines. All the angles are right angles. Okay, so this is space if there was nothing in it. That's how space would look if you were to try and describe it with some kind of coordinate system. All right. Now we're going to have a mass roll in from the side, and we're going to see how the mass changes the space around it. Okay, and this you can consider the mass exerting its gravitational field out into the space around it. So let's have a look at what that looks like. Okay, so you can see how the space is being warped in a sense. Okay, so space itself is being modified so that when you place an object in that modified space, something is going to happen to it. Okay, let's watch it one more time. All right, I'll pause it there. So you can see how the grid lines have been sort of sucked into the mass, I guess you could say. And this can give you a sort of an idea of why objects are attracted to one another gravitationally. Okay, if you just sort of imagine something being in this space here, it's going to it's very difficult to describe without getting into way too much extra detail, but you can consider the mass that you might place here as sort of bending towards the mass that's creating the gravitational field in the first place. Okay, we're getting way ahead of ourselves. This is really trying to describe maybe what general relativity looks like. Okay, but this is basically how a field works. Okay, it modifies the space around an object so that when you place an object in the field, something happens to it. Okay. All right. Now there's one more thing which I'll show you in a second. So let's get back to the PowerPoint. I'm going to mute the mic for just one moment. Okay, so you saw how that mass warped that gravitational, or that mass created a gravitational field by warping the space around it. Okay, that's how you want to try and think about it. Okay, now that's really hard to draw and really hard to try and describe to someone. So we're going to simplify things a little bit, and we're going to treat the gravitational field as a vector. Okay, so vector has both a magnitude and a direction. Now, if you think about what happens, say, here's the Earth, all right, and you place an object above the Earth, say, over there, think about what direction that object might start moving, okay? And you probably know it's going to be, it's going to start moving down towards the Earth, yeah? If you place the object further away from the Earth, you might imagine that it's not going to be pulled as strong towards the Earth, but it should still get pulled towards the Earth with some smaller force, okay? So you can see, if you consider these things as vectors, it's just telling you that objects which are, or so rather space that is closer to a mass, has stronger gravitational field because objects are pulled more strongly towards this central mass. Objects further, or rather space that is further away, has a weaker gravitational field because objects in those further away spaces get attracted more weakly towards that central mass, okay? So we can consider the gravitational field itself as a vector. And the field, you've got to remember, makes things happen to objects that are in the field, okay? And the thing that it makes happen to those objects is it gives them a force. All right? So the magnitude of these arrows here, we're going to refer to as the field strength, and the direction just tells you which direction the force on an object will be exerted, just like we've drawn in our picture here. All right, now for gravitational fields, it's really important to remember the fact that they are always attractive. Okay, masses are always attracted to one another. They are never repelled by one another in terms of gravity. Okay, so if I put an object on this side of the Earth, it's going to be attracted that way. A bit further out, it'll still be attracted, just a bit more weak. If I put an object on the left-hand side here, it'll be attracted that way. Okay, so it's always going to be attractive. And these field line vector thingies that we're drawing here are always going to be pointing towards the center of mass of the object that's creating or exerting the field in the first place. All right? So we say that the gravitational field is attractive, never repulsive. Okay, and we can have a discussion about antimatter and dark energy and things like that. We actually don't know whether antimatter interacts any differently in terms of its gravitation. Okay, we currently think that antimatter just has normal gravity, like what we're used to. But there is this theory about this thing called dark energy, which can sort of explain how the universe is accelerating in its expansion and making objects fly away from each other and things like that. But let's not get into that. Okay, you can do some research for yourself. This video I'll show you in a second after I talk about the next slide. So you notice we started drawing a bunch of vectors here. Okay, so this is a way to represent the field around a mass. Okay, and we call these arrows field lines. And basically what the field lines are describing are the directions that the vectors are pointing. Okay, mainly. So that's what we've got in the first dot point here. The field lines indicates that the direction of the fields point straight down towards the center of mass. Okay. What we can also say is that closely spaced arrows indicate a strong field. So notice how very close to the mass here, the distance between the arrows is, quite small compared to when you go further out from the mass, say up here, the distance between the arrows is much larger. Okay, what that indicates to us is that the field is much more strong, say at this point here, than it is at this point here, because the space between the arrows is closer down here than it is up here. All right. Later on, we'll talk about uniform fields, and all that would mean is that all the arrows are pointing in the same direction, and we'll see a situation in which that applies. Okay. Now, here's the thing. Technically, an infinite number of field lines could be drawn. Okay, I could just draw another field line here, like that, or another one here like that, and all these spaces in between, I could just keep drawing field lines pointing down towards the mass, but we don't have to. You only have to draw a certain number of field lines to get a sense of which direction the gravitational field is pointing. Okay, you don't have to draw so many, you just have to draw enough so that someone could get a general idea of what's going on. Okay, in this case, drawing enough arrows shows us that the gravitational field always points towards the center of the object. Okay, so that's pretty much it. That's how we're going to represent fields. So let's just do a quick question. So the diagram shows gravitational field of a planet. Use arrows to indicate the direction of the force the field would exert at points A, B, and C, and indicate the relative strength of the field at each point with the length of the arrow. So A, a little bit far away, so it'll feel a force just not as strong in that direction there. Okay, so we draw a little arrow but pointing towards the center of the planet. B is much closer, so it's going to be in a much stronger gravitational field, so it will experience a much stronger force. So to indicate that, we draw a larger arrow pointing again towards the center of the object. And C is kind of around the same distance as A, maybe slightly closer, so we'll draw a slightly longer arrow, but not as long as B, because it is still further away. Okay, and again, it points straight to the center of that object. Okay, so what these arrows here are representing might be the forces that these objects placed at these 3 points might experience. Okay. Now, what happens when you've got multiple objects around each other? How do you draw the field lines there? Well, you've got to remember, the gravitational field we're representing as a vector. Okay, so what you could do if you really wanted to, and you're never really going to be doing this because it's a bit too complicated for at least gravitational objects. Draw all the gravitational field lines for the Earth around the Earth. Okay, so you might draw that one there, that one there, that one there. You might draw a whole bunch here, as in what's going on there. And then do the same thing for the Moon. Okay, however, you've got to remember the field is a vector. So the Moon would exert its own gravitational field. Well, let's pick a point somewhere in this region where all the arrows are, okay? So the Earth would exert a field at this point, whoops, down that way, towards the Earth. The Moon would also exert a field at the same point, down that way towards the Moon. Now, the Moon's smaller, so you can imagine the field is going to be slightly weaker, all right? And we'll see qualitatively in a second how we can work it out. Quantitatively. But these are vectors. You can add these two vectors together and you can produce a net vector which might point somewhere down that way. And you can see that that's kind of the direction this little arrow in there is pointing. It's just that I've drawn my arrows slightly too big. But we're always just adding the vectors of the field for each object that's in our system. Okay, now you're not going to get any more complicated than two objects. But, for example, this is what the gravitational field lines would look like around the Earth and the Moon. Okay? So we always add the gravitational fields from separate objects together vectorially. Now, this part right here is really interesting. Okay? You can imagine that, you know, all these arrows along this line here, this vertical line, well, down here they're pointing upwards. Up here they're pointing downwards. What's going to happen in the middle? Well, you might imagine they cancel out. Same thing along this horizontal line. The field lines on the right-hand side are pointing towards the Moon. The field lines on the left-hand side are pointing towards the Earth. But right in the middle, they might cancel out. So what's going on there? Well, at that point, a very special point, the gravitational fields from both the Earth and the Moon cancel each other out. So there is no gravitational field at that point. Or rather, there's no net gravitational field at that point. And sometimes that can happen. Okay, and what would happen if this was a perfect system, there were no other objects in the universe, putting an object right there, it's going to be basically being pulled towards the Earth with the same strength as it's being pulled towards the Moon. And it's not going to move in either direction. So the net force is going to be zero, it won't move. That's what happens. Okay. It's also really important to know that when you draw your field lines, they never cross over each other. Okay, you don't draw a field line like that and then another one pointing down that way. What you've done there is you've probably drawn your arrows too big. So if you wanted to, you could redraw them and go, yep, the field at that point points down that way. The field at that point points down that way. Okay, and that'll solve your problem. Okay, but field lines never cross. If you wanted to work the field in the middle here, it's not, you know, that one extending and pointing that way and that one extending and pointing that way. You've got to add them together. And so the net field at that point might be straight down. Who knows? Okay, it depends on the situation, but you never make them cross over each other. That's just sloppy physics. All right, so this is our gravitational field. All right, it's a way to describe how objects experience and force without contact. Okay, so an object creates a field out in the space around it. You put another object in that field, and based on the warped nature of the space due to the field, the object that you place in the field will have something happen to it. In this case, it's going to experience a force. We say that for objects and gravitational fields that the field lines point radially inwards. Okay, so they're all just pointing towards the center of the object that's creating the field. That's what the gravitational field lines would look like. So we say that the field points radially inward. And we can represent gravitational fields with field lines. Finally, gravitational fields are always attractive. We're never going to be talking about repulsive gravitational fields. Anyway, that's our introduction to fields. Now we're going to start looking more at how we can work quantitatively with them, calculate strengths and things like that. So hopefully this now gives you a bit of an idea of what causes a force between two objects that aren't in contact. Okay, it's all to do with this field modifying the space or spaces around the objects. Okay. So here's just some questions to think about. I've answered these questions on OneNote, so you can go and read my responses there, but these are just some things to think about, and if you think about them and try and give an answer and compare it to what I've written, then that means you've understood what's going on. Okay, so have a read of them, try and answer them yourself, and there you go. Okay, so stop there. Next video, we'll look at how we can work quantitatively with gravitational fields. All right, see you then.